Hey, good morning, everybody. This is Mr. Ainsworth, and we're going to get into Section 2 of Chapter 2 here on the basic differentiation rules. That's a big word here today. And we have a lot of things to do, so take a look at the goals here. You can read them on your own here. We have to develop the derivative of a constant, be able to find that. We have to talk about what's called the power rule, the constant multiple rule, be able to take derivatives of sums and differences, and also the trig functions as well. So we have a lot to do. Let's get started here. What we want to do is first learn how to take the derivative of a constant. And we have a theorem here. It's theorem 2-2 in your book, or 2.2. I directly correspond with the book here. And it states that the derivative of a constant is 0. And the constant could be any real number here. Any real number. So the derivative of 5 is 0, the derivative of 6 is 0, the derivative of pi is 0. All right, and the derivative of c, where c is any real number, is also 0. Remember, d dx, the derivative of c in respect to x, is equal to 0 here. Okay, so if you, to get started here, what you want to do is you want to start off with a function. So you say let y equals c, where c represents some constant. Or you can write it as f of x equals c. Remember, y and f of x are the same thing. Okay, where c is some real number. Let's write that down. Where c is any real number. And so you start off with a general function where c is a constant, and you take a derivative and apply the limit definition of the derivative. Now I'm going to state the limit definition over here of the derivative. So y prime, or f prime, it really doesn't matter, y prime, they're synonymous there, is equal to the limit as delta x approaches 0 of f of x plus delta x minus the function itself, all right, divided by delta x. And that's called the limit definition of the derivative, which we developed in last section here. And what we want to do is apply that to the function y equals c, or f of x equals c. And so here we go. Let's go for it. So y prime, or you can write it as dy dx, the derivative of y in respect to x, is equal to d dx, that's how you say it in short terms, of the function c, because y equals c here, which is equal to the limit as delta x approaches 0 of f of x plus delta x, which is the function evaluated at f of x plus delta x, minus the function itself, all divided by delta x. All right, now that's going to be equal to the limit as delta x approaches 0. Now when you substitute the x plus delta x into the function, no matter what you substitute in, you're going to get c, all right, because it's a constant function. So that's going to be equal to c minus the function itself. Okay, what's the function? Well, it's equal to c, so c minus c, all divided by delta x. And that's going to be equal to the limit as delta x approaches 0 of 0 divided by delta x, which is just 0. And remember that the limit of 0 as delta x approaches anything is equal to 0, because the limit of a constant equals a constant itself. So when you take the derivative of which is d dx of a constant, the derivative of a constant, you get 0. I don't care what that constant is, you're going to get 0. So for example, in number 1 here, the function y equals 4, that's a constant function. So y prime equals 0. Here, f of x is equal to 2. So f prime of x, that's prime, is equal to 0. And s of t equals negative 5. Well, negative 5 is a real number too. It's constant. So s prime of t is equal to 0. When you take the derivative of a constant, you always get 0. The next basic rule is called the power rule, and that tells you how to take a derivative of a polynomial function, or any function raised to some power. If n is a rational number, so it could be fractional, okay, f of x, given the function f of x equals x to the nth power, is differentiable, and f prime, this should be a prime right here, f prime of x equals n times x to the power of n minus 1. Now the proof involves the binomial theorem, and I'm not going to prove it here, we're just going to apply it. Okay? So remember, the exponent can be a rational number, which means it can be an integral, an integer, positive or negative, or it can be a fraction, a over b. That's what it means by rational number here. Okay, and in this case right here, we're given that in our first case here, f of x equals x to the fourth, our derivative f, which is called f prime, is going to be equal to 4 times x to the 4 minus 1. Again, what I'm doing is I'm applying the derivative rule on x to the n. It's called the power rule. Okay, well, that's equivalent to 4x cubed. Okay, now that represents the slope of the tangent line at any point. Remember that. I'm going to write that down. The slope of the tangent line at any point. At any point. So what they're going to have you do is find the derivative, which gives you the slope of the tangent line, and then evaluate that derivative at a particular x value, in this case x is equals 1, and you're going to get the slope, and that's 4 times 1 cubed, which is obviously a 4. Okay, so you're going to be evaluating derivatives to get to the slope at any point you want. The next one here, q prime, is going to be equal to 4/3 times x to the 4/3 minus 1, and that's equivalent to 4/3 times x to the, let me see, 4/3 minus 1 is 4/3 minus 3/3, which is 1/3. All right, and you want to evaluate that at x equals 1 again, and then you take 4/3 times x, or excuse me, not x, but 1, because you're going to have to substitute 1 in here. All right, so 1 to the 1/3 power, which is the cube root. The cube root of 1 is 1, so you get 4/3 as your slope. Remember, we're finding the slope at x equals 1. So you just evaluate the derivative at x equals 1. Evaluate derivative, okay, at x equals 1. That's what it means. And that's what you do in order to find the slope. And then the third one here, you've got a root function. You're taking the fourth root of x. So what you want to do is rewrite exponentially. So you write it as x to the 1/4, and then you apply a power rule. So here we have y prime is equal to 1/4 times x to the 1/4 minus 1, which is 1/4 times x to the negative 3/4, which is the same as 1 divided by 4 times x to the 3/4 power. Now if you evaluate this at x equals 1, you get 1 divided by 4 times 1, or 1/4. Alright, so you got the slope, which is found by evaluating your derivative at a particular x value. In this case, we want to evaluate the slope, or the derivative at x equals 1 to find the slope. Okay, next one, we want to find the equation of the tangent line. Okay, and in order to do that, you need to find the slope and the point. Okay, you need to find the slope. Okay, and you need to find the point. Because here we want the slope, or the equation of the tangent line at x equals 1. Well, the question is, what's the point at x equals 1? So we have to do a couple things. We have to find the slope, then we have to find the point, and then we have to write the equation. Alright, so here we go. Let's find the slope by finding the derivative first. Okay, so f prime is equal to 4 times x to the 4 minus 1, or 3. That gives you the slope at any point. And now you evaluate it at x equals 1 to get 4 times 1 cubed, which is 4. And there's your slope. Slope's 4. Now the next thing you do is you find your point. Okay, now if x equals 1, then y is equal to 1 to the 4th power, because you just substitute this in here, and whenever you want to find a y value, just substitute the x value in, and you get 1. So your point is 1 comma 1. And thirdly, what you're going to do is you're going to use the point-slope equation, y minus y1 is equal to m times x minus x1, to get your equation of your tangent line, where this is x1 and this is y1, and of course this is your slope right here, m equals 1. So when you do that, you get y minus x1, which is 1, is equal to your slope of 1. Well, excuse me, this is not, so let me redo that. I was going too fast. Let me change that. That's not your slope. Okay, that's your point. Okay, so that's 1. Here's your slope right here. What am I thinking? Okay, m equals 4 here, so let me substitute 4 in. Okay, you got 4 times the quantity x minus y1, or excuse me, x minus x1, which is 1. Okay, so you have y is equal to 4 times x minus 4 plus 1. Distribute through the 4 and then add a 1. And that results into a tangent line that looks like y equals 4x. See, negative 4 plus 1 is minus 3. Okay, there's your tangent line right there. Okay, so first find the slope by finding the derivative. Evaluate the derivative at that point to get your slope. Substitute x into the function to get your y value to get your point. And then write the equation using point-slope form. And again, this is called point-slope form. Why? Well, because you need a point and a slope. The point is x1 comma y1, and your slope is m. Okay, that's why they call it point-slope form. Okay, again, x1 comma y1 is your point. And the point in this problem is this right here. All right, now moving on here a little bit, let's learn how to take the derivative of a constant times a function here. Like if y equals 4x, then how do you take the derivative of that? So here, notice that when you're taking the derivative of c times f in respect to x, or d dx of c times f, what you do is you just basically distribute out the constant right here, distribute it out, and then take the derivative of the function itself. Apply the derivative to the function. Very much like what we did in limits. All right, and the proof of that is as follows. Okay, so here we go. We're going to assume that y equals, let's see here, this is y here. We're going to let y equals c times f of x here, and we're going to take a derivative and see what happens and apply the limit definition. And again, the limit definition, y prime, is equal to the limit as the delta x approaches 0 of f of x plus delta x minus f of x, all divided by delta x. There's your limit definition. Write it down every single time, and just after repeating it a lot of times, you'll get the hang of it. So y prime in this case, or d dx, it doesn't really matter how you want to write it here, y prime, or the derivative, d dx, of c times f is equal to the limit as delta x approaches 0 of the following. Now, f of x plus delta x here, when you substitute in f of x plus delta x into the function f, you substitute it in right here, and it becomes c times f of x plus delta x. Okay, there's your first substitution. That's f of x plus delta x minus the function, which is c times f. All right. Okay, again, just look right here. This is our given function right here, y equals c times f, all divided by delta x. Well, notice in the numerator here that you have the c in common. Okay, I'm just going to factor that out. So I've got the limit as delta x approaches 0 of c times f of x plus delta x minus f, all divided by delta x. And if you remember, one of the properties in limits is that I can take this c here and distribute it out. So I can write it as c times the limit. And so this is equal to c times the limit as delta x approaches 0 of f of x plus delta x minus the function f, all divided by delta x. And guess what? That right there, this portion, that's f prime. So it's c times f prime, and I've proven everything I wanted to prove. QED, quad eris demonstratum, guys. That which was to be demonstrated. All right, so when you take a derivative of a constant c times f, just distribute out the constant and take the derivative of the function, and then you get c times the derivative, or c times f prime. Okay, so with that in mind, let's try it here. We got y equals, let me see, this is a fraction. Okay, 5 divided by x. I'm going to rewrite it exponentially first. Y is equal to 5 times x to the negative 1 power. And at this point, I'm going to take the derivative. Y prime is going to be equal to 5 times, or the derivative, d dx, of 5 times x to the negative 1. So I want to use the power rule here like I did before. And remember the power rule, it's n times x to the n minus 1. But it applies to x to the n, which notice there's no coefficient in front. Okay, so what I'm going to do is distribute out the coefficient and rewrite it as 5 times the derivative of x to the negative 1 power. Okay, and now I take the derivative, so I take 5 times negative x, oops, not negative 1, but negative x here. Let me start over. So negative 1 times x to the negative 1 minus 1, and simplify it as negative 5 times x to the negative 2, and then rewrite using positive exponents, negative 5 divided by x squared. Okay? Now in the future what's going to happen is that you're not going to go through all these steps. All you're going to do is you're going to take 5 times negative 1, take the exponent, multiply it by the leading coefficient, so 5 times negative 1, and write down negative 5, and then subtract 1 from the exponent, make it become negative 2, and then rewrite using positive exponents. That's always going to happen. Alright, but as you're learning, you can try it this way first. And then here we have f of t is equal to 6 times t to the 1/2 power. So notice I write exponentially first. And then when I find f prime of t, I'm going to take 6 times the derivative of, in this case, d dt, not d dx, because we're taking it in respect to t now, of t to the 1/2 power. And that's going to be equal to 6 times 1/2 times t to the 1/2 minus 1. Well, we know that 6 times 1/2 is 3. 1/2 minus 1 is negative 1/2. And then you rewrite it using positive exponents, 3 divided by root t. Because you move when you have a negative exponent, you shift it in the denominator, so you get t to the 1/2. And t to the 1/2 is just root t. Okay. So now what you need to do is learn how to take the derivative of a sum and difference. So what I'm going to do is first just show how the derivative of a sum equals the sum of the derivatives, and then it's pretty much synonymous for the difference rule too. So a proof of the sum rule. Okay, and the same thing applies to the difference rule. All right, so we're going to let y equals f plus g. Okay, y is the sum of two functions. It could be x squared plus 3x. It could be any sum of two functions here. It really doesn't matter what it is. It's just f and g just stand for two different functions. And we want to find the derivative, find y prime. Find the derivative, find y prime or dy dx. Okay, so let's do that here. Let's go for it. I'm going to start off with the derivative of y, but y is f plus g. Okay, and I'm going to apply the limit definition. So this is going to be equal to the limit as delta x approaches 0 of the function evaluated at x plus delta x first. And our function here, y, is actually f plus g. So I need to substitute x plus delta x in two locations, here and here. So here we go. So f of x plus delta x plus g evaluated at x plus delta x. Alright, and now I have to subtract the function itself, which is f plus g. So f of x plus g of x, all divided by delta x. Okay, and now I have to get a little creative here and rearrange some things. So I'm going to distribute through the minus sign and rearrange terms. So I'm going to have the limit as delta x approaches 0. And I'm going to distribute through the minus and rearrange. I'm going to group up the f's and I'm going to group up the g's. So f of x plus delta x minus f of x, because I have to distribute through the minus sign. And then plus, because there's a plus sign here, g of x plus delta x minus g of x, all divided by delta x. And so what I need to do now is I need to get creative. I need to split the fraction here. Okay, I'm going to take this to f, all the f's, f of x plus delta x minus fx, divide that by delta x, and then I'm going to do the same thing here. I'm going to take the g's divided by delta x. I'm going to split the fraction. Okay, so the limit as delta x approaches 0 of my first fraction divided by delta x, and then plus, once again, let me highlight that. This is plus right here. The limit as delta x approaches 0 of my g's, so g of x plus delta x minus g divided by delta x. And notice that these are both limit definitions of the derivative, so this is equal to f prime plus g prime. So the derivative of a sum equals the sum of the derivatives. One more time, the derivative of the sum equals the sum of the two derivatives. Piece of cake. QED. All right, quod eris demonstratum, that which was to be demonstrated. Okay, now you notice that we got a sum and difference of functions here. So we just take the derivative of each piece, basically. So f prime is going to be equal to, and again, this is using the power rule here, and that means the derivative of, let me see, d dx, or the derivative of x to the nth power, is equal to n times x to the n minus 1. There's your power rule. It's equal to 5x to the 5 minus 1, or 4th power, minus 3 times the derivative of x squared, which is just 2x, plus the derivative of a constant, which is 0. And so what you get is 5x to the 4th minus 6x for f prime. Okay, and now what you have to do is find the derivatives of sine and cosine. And it states here, the theorem states that the derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, so why is that? Well, we're not going to just accept it in this class. We're going to prove it. Aha! So I'll tell you what. Bring it on. Okay, so let's go ahead and do that. Let's turn the page here and let's prove why the derivative of sine x is cosine x, and then afterwards we'll prove the other one. All right, and here we go. We're going to do it by using the limit definition. So the derivative of sine x is equal to the limit as delta x approaches 0 of the function evaluated x plus delta x. So I need to take sine evaluated x plus delta x first. Now and then I go minus the function itself, sine x, all divided by delta x. You know what, let me pause for a second. Let me rewrite it over here, the limit definition of the derivative again, just so you can see it in front of you here. So the limit as delta x approaches 0 of f plus x plus delta x minus the function itself divided by delta x. And again, that's called the limit definition of the derivative. Okay, so remember that. Okay, it will be on the test. All right, I'm going to ask you to write it. And then apply it. Okay, so now what we need to do is something from last semester. We have to work on this, and I'll tell you what we have. You guys remember the what we know what we know about the sine of alpha plus beta. So let me just recall something here real quick. The sine of alpha plus beta last semester in pre-calc was the sine of alpha times the sine, times the cosine. It alternates. Going too fast here. Times the cosine of the second angle beta, all right, plus the cosine of alpha times the sine of beta. Okay, remember the sign alternates there, or the functions alternate in their pattern, and then the sign remains the same. So what I need to do that is expand sine here. Okay, so this is equal to the limit as delta x approaches 0 of sine x times cosine delta x plus cosine x times sine delta x, okay, minus the function here. Remember that. This portion is the same. And then all divided by delta x. And then I have to somehow get creative here to generate a cosine. So what I'm notice here is that the function here, the first function here, let me highlight it here, there's sine x involved here and here. So I'm going to group up those terms and I'm going to distribute out the sign and see if I can find any special limits because they're hidden in here. So I'm going to take the limit as delta x approaches 0 of sine x times cosine delta x minus sine x. I'm just going to bring this over here and rewrite the terms. Plus, I'm going to bring that term over on the right, plus cosine x times sine delta x, all divided by delta x. Okay, and then what I want to do is I want to split the fraction again. I want to take all of this divided by delta x, and then I want to take all of this and divide it by delta x, and I'm going to split the fraction. So I take the limit as delta x approaches 0. Oops, too long of a fraction bar there. There we go. Let me see, sine x times cosine delta x minus sine x, all divided by delta x. And then what? Look at here. Plus limit as delta x approaches 0 of cosine x times sine delta x, all divided by delta x. I split the fraction. And what's cool about that is that I found some special limits in here that we learned from last chapter. Alright, I'm kind of running into the next one here, but you know what? I need to step it out for you guys, so I'm not going to skip any steps. Okay, so I'll just create some more room later on. So the limit as delta x approaches 0 of sine x, I got to distribute it out, times cosine delta x minus 1, all divided by delta x, plus this other guy. And now, here's something tricky here. We're taking the limit as delta x approaches 0. And notice this function here, cosine x, does not involve delta x, it involves x. When that happens, you consider this function here, the one in yellow, the cosine x, as a constant. And we learned that when we deal with constants and limits, we can distribute the constant out. So I can distribute this function out here like this. Same thing here, I can distribute that function out there too, because we're taking the limit as delta x approaches 0. So sine x is considered to be a constant in this case, and we can always distribute constants out of the limit. So what I'm going to get is cosine x times the limit as delta x approaches 0 of sine of delta x divided by delta x. And this should look familiar. That right there is a special limit, and it equals 1. Okay? That equals 1. And then when I distribute out the sine x, I get sine x times the limit as delta x approaches 0 of cosine delta x minus 1 divided by delta x. And that right there is a special limit, and it's equal to 0. So I have sine x times 0 plus cosine x times 1, and that's obviously cosine x. And then I'm done with my proof. Okay? I just proved that the derivative of sine in the very beginning is equal to cosine x. Okay, we're going to do that too, again with cosine x here. And we need some room, so let's see here. Okay, so we'll do the proof over here. This one is very much similar here. You know what I'm going to do is I'm going to stop the video here actually, and I'm going to have you guys do this, and I'll check you in class. I'll leave this to you. It's very, very much similar to what I just did here. All right, it involves special limits, and but this one turns out to be negative sine x instead. So I'm going to leave this up to the student. Leave it to the student to do in class. In the class is similar to the previous one. All right, I'll check you in class. Check with teacher. All right. I can't do everything for you, so you try that one. All right. And now let's apply it here. The function g, okay, notice it's a sum and difference of polynomial functions and trig functions, but you're just going to take the derivative of each one. So g prime is equal to 3 times the derivative of x squared, which is 2x, using the power rule, minus 2 times the derivative of sine x, which I said is cosine x, plus 7 times the derivative of cosine, which is negative sine. Okay, and then you just go ahead and rewrite these things. 6x here, minus 2 cosine x, minus 7 sine x. Okay, and there's g prime, the derivative. This represents the slope of the tangent line at any point. Okay. And lastly, what we need to do is find the equation of the tangent line. The equation here. And because of that, I need the slope. I need slope. I need the slope and a point. And a point. Okay, so the slope first. Okay, and you do that by taking y prime and evaluating it. So y prime, the derivative of sine, is cosine x. It's that simple. Evaluate it at x equals 5 pi fourths. So that's cosine of 5 pi fourths. And that's quadrant 3. That's 1 and a fourth pi. That's quadrant 3. Cosine's negative there. And the reference angle is pi fourths. So you get negative cosine of the reference angle. And that will give you negative root 2 divided by 2. Okay, and then what you do is you find the point. So second, you find the point of tangency. So when x is 5 pi fourths, if x is 5 pi fourths, then y equals f of 5 pi fourths, which is which is sine 5 pi fourths, and that's negative 2 because you're in quadrant 3. Sine's negative there, and so you're going to get negative rad 2 to 2 again. And then you write the equation. Step 3, write the equation. So y minus y1, which is your x coordinate, y minus y1, which is your y coordinate, which is negative root 2 over 2. So let me change that. So negative rad 2 over 2, watch the double negative there, is equal to the slope, which is negative rad 2 over 2. Remember, slopes don't have to be whole numbers or negative or positive. They can be anything. So negative root 2 divided by 2 times x minus x1, which is 5 pi fourths. And if you want to simplify this a little bit, you get y is equal to negative rad 2 divided by 2x. That's when you distribute here, and then when you distribute again, you get plus, let me see, 5 pi root 2 divided by 8, and then subtract the root 2 over 2, root 2 over 2. So crazy looking equation there, but hey, there's your tangent line. In calculus, anything can happen. Okay? So give your homework a shot. And come to class tomorrow with some questions, and I'll help you out. See you then.